Now for our last video, or maybe not our last, there might be one more for fun. Problem 11. The woman, take her as a small little body, standing on the end of a plank on a smooth, frictionless surface, ice or something like that. She jumps off perpendicular to this board. She goes off in some direction, the direction perpendicular to the board, and then the board then its center has to go opposite to her, and you can see that when she jumps off, she's kind of pushing against it, so it will recoil and rotate this way. And so drawing a picture at the very beginning really helps. We have the general rigid body story that the center mass is moving constantly and rotating constantly around the center of mass. No external forces horizontally. Momentum's conserved. Initial momentum is final momentum, and that helps me figure out these velocities. In fact, there are no individual forces at all, so that there can be no torque at all around any point P. You could have forces balanced but still have a torque because the forces were applied at different places, different lever arms. But there's no forces at all here. So angular momentum is conserved. The initial angular momentum equals the final angular momentum, and this is just a nice single, we can take a specific single axis around which we'll define, a point P around which we'll define our angular momentum. By the way, first point, kinetic energy is certainly not conserved here. She's got her own energy that she's putting into this thing. So mechanical energy is not conserved. Over the overall universe, energy is conserved, but not mechanical. That's a number one thing to be careful of. Don't take kinetic energy conserved in anything until you know it's frictionless, conservative. Everything is absolutely non-dissipative. Secondly, don't go throwing around equations like V equals omega R here, like this V is omega L over 2, because this is not rolling. This isn't a ball. This isn't locked in at all. This omega can be completely independent of that V. This omega we're going to find from angular momentum conservation. That V we found, or can find, from momentum conservation, linear momentum conservation. Now, I'm going to do a different point P than in the solution, just so you can see everything works out to be the same. The angular momentum of the woman is just mv, distance of closest approach, where I'm taking my point P to be the original center of the stick of the board. So it's sort of like here now. And her distance of closest approach to that is L over 2. What about the sign? Well, the cute little homely way of thinking of it is, if somebody's coming like this below that point, it would tend to hit, if it hit anything, it would tend to make it spin clockwise. I'll put a minus sign there. That checks with R cross P. If I take R, actually I can take R at any point here. Let's say after she's gotten down to here, if I take R cross P, there's my R, and then her P is like that. And if I put the P up here so I can see it more easily, if I do my R cross P, if I do my blue crayon and turn from R to P, it goes into the paper. That corresponds, remember, into the paper corresponds to clockwise spinning. And so this axis here corresponds to that. So out of the paper here would be, right-handed rule would be counterclockwise spinning. And so I've got a minus sign there, mv L over 2. The angular momentum for the plank is the translational part, as if it were squished to a point, but that's around the point P, and its center of mass goes right through P. That's the nice thing about choosing that point. It goes right through it. Its distance to closest approach is 0. That's out. And I just have the angular momentum about the center of mass, the I omega. Defining my omega this way from my picture is a plus sign, because that's counterclockwise. Of course, if I'm wrong with my picture, then omega will come out negative. And that gives you the same equation as in my solution. So just going back and forth, the difference between the translational parts is independent of point P. And this internal part is independent of point P. So the answers are independent of point P. By the way, when I was calculating the velocity of the bottom of the plank relative to ice, as the bottom relative to the plank plus the plank relative to the ice, well, this is just, the plank center of mass. This is just moving at the Planck's velocity in the x direction, if I call the x direction to the right positive. And this guy right at that instant, right when it first starts, it's getting hit that way, so that's also positive x direction. So that these two vectors are easy to add here. Later on, it starts to have an angle to it. It would be a little bit more involved. Finally, problem 12. This is fun. I got a big galaxy, and I'm imagining I've got a whole bunch of stars, and in fact, I've got a uniform distribution of stars, or some matter anyway, and inside a radius r. So I'm just going to think of a constant continuous density rho, mass per unit volume inside there. And let's suppose I crawl inside here and I've got a single star here, and I want to think, what's the force on that star? Here's the wonderful thing. Say, here's my star, mass little m. I ignore, for this spherically symmetric, nice, constant, uniform thing, I can ignore the shell outside the radius that I'm at that moment, little r. And all the stuff inside, I can act as if it's a center. So this whole thing, if the mass inside here is some little wiggle script m, this force on that little m at some r is equivalent to the force between that little m at r from a point where all the mass inside the shell is squished to a point. And oh wow, that's easy. Then the force on little m is just g little m, the big script m over r squared. But wait a minute, big M is a spherical volume 4/3 pi r cubed, that's the r we're inside of, or we're right on the edge of rather, times rho. So this goes like r cubed, this is 1 over r squared, so F is proportional to r. F grows like r as we go away from the center. Now, you remember for when you're going in a circle, v squared is just g, the mass of the earth, the mass of the sun, or whatever, over r. Well, that mass, of course, we said was proportional to r cubed, so 1 over r goes like r squared, so v is proportional to r. V grows as r grows. V gets larger as we go out. But on the other hand, if I were outside of any, mass that I thought was there, if I'm outside here, remember this whole thing could be squished to a point then, I would get that the force due to this on me being outside here would be g little m, big M over r squared, where m is now fixed, big capital M is fixed, and this thing goes like r squared, drops like 1 over r squared. So v squared is gm over r, just like we've been doing with satellites for a long time. So v drops as r goes down. So here it is. If we didn't see anything, we'd expect to see, if we didn't see much, we had just a few stars around here or there, we'd expect to see the velocity of, given star that we're looking at to go down as we go away from all the luminous matter. It doesn't. It actually goes, well, constant almost, because the distribution is not just a simple spherical uniform, telling us that there's something here, there's more here, there's more stuff making up a bigger sphere, some dark matter giving us a velocity that doesn't drop as r goes. And we see it in this model where the velocity can grow if we had some dark matter around. The discrepancy in the velocity curves is the dark matter evidence. There seems to be more stuff out here holding it in than just the stars that we can see. And that's it for now.